Hey guys, welcome back. In this video, I will mainly talk about the concept of multiple beams. So how we can form multiple beams at the same time from the antennas. So the thing is that in the previous video, to relate how the precoding vectors are going to influence the RF beam, I was speaking about the concept of beam formation, the concept of analog beam forming, and how to steer the beam to a different angle and things like that, right? So related to that, in this video, I will talk about one more important aspect, that is forming multiple beams at the same time. And in the previous video, I was mentioning that to form the multiple beams, we need to have a signal of this form. Okay. To write it in a generic way, what I would say is I can write these equations as shown here. Okay, so I can take s1 of t common and I can write it something like this. This one says that this is also should be written like e to the power of j5, but the phi is 0 degree, so this will become actually 1, so I've written it 1 plus s2 of t, and I have written it like this. Okay, so these two signals should be given to both the antennas. Now depending upon the angle, okay, depending upon the angle, we can get the beams in the different direction, and this is one signal, this is another signal, so these two signals will form the beam in two different directions. So for that, let me take an example, because in the previous video I had taken the example where, to form the beam at 30 degree. Okay, so this is theta a, which is equal to 30 degree. Sine 30 is off, so based on that I had calculated that the phi is 90 degree. Similarly, if I want to give minus 30 degree, then I have to give minus 90 degree. So based on that, this vector would become 1 and j 90, and this would become 1 and j minus 90. So with this, how would my beam look like? So this is antenna 1. Okay, this box is, let's say, antenna 1, this box is antenna 2. Now along the both side, if we take on at 30 degree angle, we have one beam. Let's say this is beam number 1. At minus 30 degree, we have beam number 2. All right, so I think this will ensure that the two beams are formed at the same time. Okay, I hope you got this clarity. But here we need to understand one very important aspect, that when these two beams are formed, the side lobe levels of one beam would interfere with the other beam, or some portion of the main lobes might interfere with the other beams depending upon the angle separation. So here the angle separation is 60 degree between the beams, right? Mainly the main lobes. So what happens if they are interfering? Then the recovery of the signal at the receiver would become complex, right? So then what would be the better strategy? We should ensure that these two beams are sufficiently apart, and one of the cases which we usually know is we need to achieve orthogonality. So let's say one beam is 45 degree, another beam is minus 45 degree, then the beam separation, especially the main lobe, would be 90 degree. So these two beams are orthogonal to each other, right? So if these two beams are orthogonal to each other, then one beam can be allocated to UV number 1, another beam can be allocated to UV number 2, in which case we can go for performing multi-user MIMO for these two UVs. These two UVs can be paired, and they can be exercised with multi-user MIMO concept, which means that both UV number 1 and UV number 2 would be allocated all the available subcarriers in the bandwidth, and we can ensure that both of them are achieving a higher throughput. But let's say if the beams are not orthogonal, then how would we achieve the orthogonality between the UVs? Then definitely among the available subcarriers, we need to divide a few subcarriers to one UV and a few other subcarriers to other UV, and we have to achieve the orthogonality in terms of number of subcarriers. So this is nothing but FDM, frequency division multiplexed multiple UVs. Okay. Um, so in terms of orthogonality, uh, we need to understand one more aspect, that is if we use the right kind of vectors. See here we have vector, right? Let's say this is a vector 1, this is vector 2. So here we are giving some appropriate phases to different antennas. Like that, if we can have a different variation of these vectors, what we can achieve is, we can achieve the orthogonal beams, and we can ensure that the beams are sufficiently separated apart. Okay, so to say that these two beams are orthogonal, what is the other concept that is required? So when, let's say, this beam number one is formed, okay, so this beam number one should ensure that the null of this beam occurs whenever there is a peak of main lobe of other beam. Got it? So similarly, the beam or side lobe from other beam should also happen. Okay. So in other words, what I would say is, you are very much familiar, let's say very much familiar with OFDM, right? So we have multiple subcarriers. What is that we gonna do? Let's say this is one subcarrier. Okay, then let's say this is another subcarrier. This is another subcarrier. So for the first subcarrier, what do we need to ensure? So already the second subcarrier's null is coming at the place where we have the peak of the first subcarrier. Similarly, for third subcarrier, null should come at the peak of the first subcarrier. Similarly, if we have the fourth subcarrier, its null should also come at the peak. So all the nulls, all the zero crossings should occur at the peak of the first subcarrier, right? On a similar line, so here also we should ensure that if we have multiple beams, then the null of all the other beams, let's say this is also another beam, all the other null of all the other beams should fall in the direction where we have the peak of the, let's say, a peak of the other beam, or let's say the first beam here in this case. Okay, so I hope you got this clarity. This will also ensure that these two beams are orthogonal, and this can also be exercised for multi-user MIMO concept. Okay, I hope this is clear to you. Multiple beams, both the concept is clear. And yeah, so equation wise also you got to know. Okay, now these vectors, right? Here I was mentioning these vectors. So here you note that even right now I'm speaking about the analog beamforming only, right? Using analog beamforming, how we can form the multiple beams in the different directions. So these phases we are going to give to the phase shifters. So in the upcoming video, we will see how using the pre-coding vectors we can achieve the beams in a different direction. Okay, how it is actually influencing the RF beam, we will see that. For that only actually we are speaking all these things. That is one point. So from the previous concept, okay, previous concept I was talking about especially the beam steering, right? So where I was mentioning that we need to give appropriate phase to this. There, I want to talk about the generic case, because the last time I had spoken only about two antennas. This is antenna number one and this is antenna number two. Okay, so when I want to have a 30-degree beam steering angle, then I was mentioning that to the signal in the first antenna, which has to travel a longer distance, right? There we have to give the phase shift of 90 degree. This I had derived here, right? This 90 degree I was giving to this antenna number one. So similarly, like what happens? So if we have multiple antennas, see, first of all, we need to ensure that if we have, okay, for first let's talk about multiple antennas. Okay, so let's say this is one antenna, so two, three, four, like that. Let's say I have one, two, three, let's say. Okay, So now I want to form the beam, 30 degree. I will take the same example. Okay, in this direction I want to form the beam. Then what should I do? I know that this one 0 degree, so this has to travel. Okay, now if I draw that all of the signals should go something like this. Then if you see, if I draw the perpendicular line, okay, so if I draw the perpendicular line to this, if you see, this has to travel longer distance and a little bit less here, less compared to eighth antenna, basically, which means that for two antenna case, what did I derive? If I have to give 0 degree, this I have to give 90 degree, right? So for third antenna I have to give 2 into 90. For fourth antenna I have to give 3 into 90. So similarly for eighth antenna I have to give 7 into 90. Okay, so this is how I should be giving the phase angles across the antennas if you are using more number of antennas, and if you want to steer the beam to a different direction. More angle, because the signal has to travel longer distance, as we had seen that the distance lambda and angle are related. Okay, 360 degree both are related. This we had seen in the previous video. So I hope this is clear. But now I want to talk about one more architecture, because see, when we have these many antennas, right? So we cannot ensure that in some cases all the eight antennas have different RF chains. So let us say now I have only number of layers which needs to be supported is two. Definitely in this case we should have two RF chains. Okay. So RF chain. RF chain, because it consists of power amplifier, local oscillator, and things like that, it would be very costly to have more number of RF chains. So number of layers is equal to 2. Let's say I've got two RF chains. Now these two RF chains, now how can I divide into 8 antennas? Now we need to definitely have a equipment here, that is power divider. I will call it as PD. This should be 1 is to 4 power divider. Okay, here also I should have 1 is to 4 power divider. Then I will get 4 outputs. This 4 output should go to 4 different antennas. Okay, but we know that across each antenna we need to have a relative phase shift. So definitely the phase shifters, at least this one phase shifter should be separate for each of these antennas. Okay. So similarly, I can go for four numbers on this device as well. Okay. So I hope you got it. The different architecture. Earlier, I was mentioning that we can have only phase shifters, but to reduce the number of chains, which is required to support the required number of layers, we can have one more component, that is a power divider in between, and ensure that here we can achieve the required analog beamforming. Okay. So I hope you got this clarity. More the number of antenna, what are the advantages? The advantages is that we can have more focused pencil beam, okay, and which would travel for a longer distance. And we need this kind of application mainly for millimeter waves, because at millimeter waves the path loss is very high. So in the upcoming videos, we will see more concepts related to uh, basically, we will see the pre-coding, okay, pre-coding based beamforming, how that is going to influence the RF beam. Okay, by that way, even we will see what do you mean by what do you mean by hybrid beamforming. Thank you very much. Have a great day. Please to subscribe to the channel.